sure we're going live here. Okay, we're live. Stop it. We are live. We're just waiting on viewers. Casey Moore's here. Hello, Casey. Maybe I should do the whole thing like this, where you can't see me like at all. Scooch in here. I've got so many wires.
7 viewers.
All right. Oh wow. Okay. Cool. Welcome everybody. Thank you for being here with us as we go over the good stuff that happened in 2020. Right. So 2020 was no, Casey. Thank you. 2020 was an interesting year altogether. So much got glossed over, well, understandably so, in terms of scientific discoveries and breakthroughs and stuff. I mean, we had so much else that was going on that we needed to know about, that things that typically would have made really big headlines didn't necessarily make really big headlines. And so we wanted to kind of close out 2020 with some of our favorite big news things that happened in science around the world this year. Some of them are really going to be life-changing if they ever come to fruition. And with that, I'm going to let Dr. Rivera take over, and we're going to kind of alternate back and forth.
Sure. Okay, guys, so first and foremost, these are not the only things that happen in science. These are just a few that we thought it would be important to share so that we're all aware that 2020 was not just COVID-19's year. It was actually a really interesting, really promising year in science. We have a few things from the area of chemistry, anthropology, physics, you name it, and research being done on it, and very interesting discoveries. I'm going to start off with a little bit of computer science. So the program Deepmind, which is owned by Google, has been used, or was previously used, to play against human hosts or human players in games of chess, Go, and other types of games, similar to to IBM's Watson a while back. But now they shifted their focus. They're now trying to do a little bit of AI, helping us scientists discover new things a lot faster. So one of the big things that Deepmind has done is crack how to predict protein folding. So protein folding, think of our proteins, which are a lot of big molecules that we have in our bodies, that plants, animals, pretty much every organic thing has all these proteins, all these structures. They are made up of a certain specific type and sequence of atoms, but they're also folded or let's say accommodated in a three-dimensional structure that determines what it does.
I'm sorry, Dr. Rivera. Can I pause you?
Sure.
I'm so sorry. Do you know how to get it off of this? Because I am totally stuck. I opened up another window, and now it's like I can't see the other one. Do you?
Yeah, you should just turn it off and on.
Okay. I'm so sorry, everybody. Go ahead, continue, please.
All right. So protein folding. Basically, when we study a protein, whatever it is, we go from simple early models such as the insulin model, for instance, to give you an example. We know how every atom is arranged and what the next atom is, right? So kind of like the links in a chain. But we want to study how those atoms fold and interact towards one another to generate the actual function, right? So Deepmind has predicted with a reasonable degree of accuracy the actual three-dimensional structure of a bunch of proteins that we really didn't know what the three-dimensional structure looked like. That is a big deal because when we isolate a protein, we can't see the actual three-dimensional structure. We just see the links in the chain. We'd have to freeze it or crystallize it. and it loses a little bit of its natural environment, which may or may not play a role in the actual structure, which in turn determines its function. So that's kind of a big deal in science. It's promising in the areas of medicinal science, in areas of material science, pretty much anything that requires us to understand the structure of something and its function. Deepmind will very likely be having a role in the near future. So that's my first big news of 2020. Michael, do you want to do one?
Absolutely.
Right.
So, of course, the chat is going. We already, if you see me keep glancing over, I'm trying to get my articles that I had up on my iPad. I should have gone old school like Dr. Rivera. So apparently 2020 has rendered me technology like.
I think you need to mention that one.
Well, it's been sat there for a little while. So yes, this year was my 10th anniversary, and it was yours too.
It was.
So in case your wife is watching too.
Yeah, June 19.
Are you sure?
Yeah.
Okay.
Yeah, that's the one thing I don't forget. I forget everything else.
So if you're in the chat and you have questions, then shoot us. Hey, Jimmy. So yeah, one of the things that I found, excuse me, really interesting this year was the number of discoveries that we found in the realm of archaeology, biology, paleontology. There were some really interesting things that happened that I'm going to be honest, I didn't know until today when we were reviewing our stuff, or yesterday when we were reviewing our stuff. So one of the things was there was the largest, or rather the longest animal ever discovered right off the coast of Australia this year. It's a Siphonophore. Now, a Siphonophore is an animal that's actually a group of animals. Think of kind of like how coral is made up of a bunch of individual polyps that work together for the greater good. You know, if the Borg were an organism,
I was thinking Borg.
these would be Borg. A Siphonophore is a very similar type of creature, and it's a living thing made up of a bunch of individual living things. Well, this particular Siphonophore was found in a canyon off the coast of Australia somewhere. I think it was Australia. And this thing was over 150 feet long. So it is, as far as the record goes, the longest animal ever discovered. That's really big, 150 feet long. It's not very thick, but if you look it up online, it's kind of like just kind of floating and coiled in the ocean. It's absolutely enormous. Another one that we found, or another thing that we found out, was that humans were in North America a lot sooner than we initially thought we were, which is going to have to cause some history books to be rewritten, because we all learned that humans crossed from Siberia into North America via a land bridge across the Bering Strait. Well, evidence shows that humans were here before that bridge actually existed, which means the only way for us to get here was by boat. So humans actually sailed here by boat. We also, at that point, hunted mammoths pretty close to extinction. And there was a trove of mammoth bones that was discovered recently in Mexico that dated from about this time period where humans would have been hunting these animals. And it's not absolutely clear, absolutely certain what happened. It looks like these animals could have gotten stuck collectively when they went to drink from a marsh. And just over time, more and more got stuck, kind of like an elephant graveyard situation. Or it could have been that humans drove them there to hunt them and to eat them. So either way, it's a really exciting discovery. Another thing, this is probably one of my favorites, is that in 2011 in Alberta, Canada, Notosaurus was uncovered. A Notosaurus is a type of ankylosaur. So if you have, an ankylosaurus, a very familiar type of animal, looks like a big turtle with a big knobby tail and everything. A Notosaurus is similar to those, right? It was this complete skeleton, so it was really intact. And as tends to happen in science, it takes a while to work through things, And so this year they found out that in that particular skeleton that was unearthed 9 years ago are the remains of its last meal fossilized in its stomach. And so we actually have fossil plants in this Notosaurus stomach, and we know exactly what it ate, which is, I mean, to me, just absolutely incredible. This not speculative, but this perfect glimpse into the past. We had so many of these types of discoveries throughout the year that I think, these aren't going to necessarily reshape humanity, but they definitely, in the future, but they definitely reshape our understanding of the past, especially when humans came to North America.
So fossilized food.
Fossilized food. For my sister's high school graduation, I love paleontology, I love archaeology, geology, all this stuff. And you know my sister. And you know that, and if those of you that are out there that know me know that I can be a little mean, but in a fun way, I guess.
I gotta go get Francine. I'll be right back.
Oh.
Guys, excuse me.
Is that what that was?
Yeah.
Sorry. So, for her high school graduation, I actually got her coprolite, which is fossilized dinosaur poop.
Sounds like a very Michael Scanlon gift.
Hey, I'm kind of jealous of it. It was really gorgeous.
Yeah.
Well, while you go do that, I'll take my next topic.
So that food, was it McDonald's? What was it? Because I've been told that stuff lasts. It doesn't decompose.
It might very well have been McDonald's in that Notosaur. I think scientists reheated it and ate it, and said it tasted like just garbage.
So was it like a Mac fossil?
It was some Mac fossil. So we do have another scientist, another person coming in. We were going to try to do this teleconferencing, but we had audio issues, and she graciously agreed to come up here and be with us. So anyway, another thing that we found this year, which is another discovery, which is pretty interesting to me. Now, I'm not a biologist, right? I'm a physicist. Dr. Rivera's a chemist, and Dr. Lemoyne, who's coming in, is a biologist. But in our nasal cavity, in our sinuses, we actually discovered a new type of organ that we didn't know was there before, and it wasn't something that was small. This thing's like 1.5 inches long. I don't remember the name of it, but I was reading the article, and I'm like, how did we miss this? I mean, aren't there like scientists who study this like for centuries? But yeah, apparently we missed an organ in our nose, sinus area. What's up? And we discovered it this year, and it was not a small one. With that, I'm going to turn this over. Thank you so much for coming in. Have a seat. So, one of the big things with 2020 was COVID, okay? And we didn't want this to be a COVID show because we've had COVID. This is about what happened while we were paying attention to COVID. But we did want to bring in somebody that could sort of explain a little bit about the vaccines that are out there. Neither one of us are qualified for that. I know I'm just going to get a shot, and that's about it. And so Dr. Francine Lemoyne has graciously agreed to teleconference in, and when the audio didn't work, she drove over here. Don't know how many laws she broke. But she's here with us now, and thank you very much, and take it away.
Okay, so let's talk a little bit about the vaccine development, right? There's already been a lot of discussion about what coronavirus is. One thing that I do want to make sure that people understand, we're referring to the disease as COVID. The virus is the coronavirus. It's actually a SARS virus, very similar to the virus that created the SARS outbreak in 2003. So just like HIV is the virus that causes AIDS, coronavirus is the virus that causes COVID-19. So COVID-19 is just the name of the disease that this pandemic is in right now. So it's to really understand what happens or what the specific nature of the vaccine is, we need to sort of backtrack just a little bit and think about what's the purpose of a vaccine. Well, vaccines are ways to trick your immune system to mount an immune response when you don't really have an infection. So what is an immune response? So our immune system's job is to scan the body and identify what is not self. Basically, anything that's not naturally occurring in the body is considered foreign, and we mount an immune response to that. Now, what is an immune response? It can be anything from a fever to the development of antibodies, which is the ultimate end goal because that provides memory. It can cause inflammation and swelling. All of these things are important for the creation of blood clots, which are needed to wall off sites of infection, and the creation of pus, which is old and dead white blood cells. All those are good signs, good things that are needed in the process of mounting an immune response. So what do you need to mount an immune response? Basically, we have to have something that's foreign in our bodies for us to be able to mount an immune response. Now, what a vaccine does is provides something that's foreign, and that foreign piece, that foreign material, is something specific to what we want to have a response against, right? So let's say, for example, for the coronavirus vaccine, it is a piece of the coronavirus. Now, in terms of vaccine development, there's been sort of a standard process of the creation of vaccines, and that involves taking a virus or a bacterial cell and either the entire thing intact or a small piece of that, a protein that's on the surface of that virus, and injecting that into a healthy individual. So now the immune system can see that as something that's foreign, and you mount an immune response. So the priority is to get a protein that the virus has on its outer surface, because that's what our body would come in contact with first to mount the immune response. So in the past, vaccine development has occurred in a couple of different ways. The sort of most primitive way was to find a virus that was similar but not identical. Think of the cowpox virus being used to provide treatment against smallpox, right? Cowpox infected cows, smallpox infected humans, and they could use cowpox injected into humans, and we would be protected from developing smallpox because they were close enough together. Well, not all viruses have a counterpart that is as easy to use. So scientists developed a new method, now new, back 40s and 50s, called attenuation, where they could take a bacteria or a virus and grow that virus in the lab in a different setting so that the virus became altered, or what we called attenuated. The best example of this was the poliovirus vaccine, the original poliovirus vaccine, where they took human poliovirus and they grew it in the lab on African green monkey kidney cells over and over and over again. And over multiple generations, they ended up producing a human virus that wasn't so good at infecting humans anymore, but was really good at infecting monkey cells. So they took this attenuated virus and injected it into humans. So now the virus was the human poliovirus, but it wasn't very good at causing an infection. It had all the same parts and pieces, the proteins on its surface, and the immune system was able to recognize it as foreign, mount an immune response, and build memory. The problem with creating attenuated vaccines is that they do have the possibility, because it's a live virus, of mutating and becoming virulent again and causing an actual infection. So that's not the best strategy to use for vaccine development. It's an option, but it's not the best strategy. So as we've become better and better at molecular biology, we've been able to develop other systems for creating vaccines. Now we use what we refer to as subunit vaccines. And a subunit vaccine, we simply take one protein of the virus, one protein that's on the outer surface of the virus, and inject that into a healthy individual. So we think about, annually we take the influenza vaccine. Those are subunit vaccines. It's pieces and parts of the proteins. It is not the intact virus, and there's no chance of ever developing an influenza infection from that type of vaccine. Okay, I'm going to say that again for the people in the back. It is scientifically impossible to develop an influenza infection from receiving the influenza vaccine. Now, again, that vaccine is a subunit vaccine. They give you a piece of the protein. So how do they get the protein? Well, in the lab, we have to trick bacterial cells into producing lots and lots and lots of these proteins that we then purify in the lab, incorporate it into a vaccine with what we call adjuvants that help to excite our immune system and mount a response. And that's what ultimately gets injected into your muscle. So one of the issues with these proteins is that proteins aren't very stable. And so we have to add preservatives and things to proteins, right? Those of you that are biology majors, remember, if we have proteins that get into environments that are more acidic or more basic or a wrong temperature, proteins start to unfold, right? And that process of denaturation is going to limit our ability to mount that immune response effectively. So what scientists have done now is take even a step further back. The ultimate end goal is to get the protein into our bodies so that we can mount a response. So what if we could trick our bodies into producing those proteins? Again, physically impossible to develop an infection by expressing these proteins, but having those proteins expressed means that now that's a foreign body inside and we can mount an immune response to it. So now we get to the mRNA vaccines. mRNA, or messenger RNA, is the precursor to the development of proteins. So our cells use this process called translation. Messenger RNA gets translated into the protein. So we have a piece of messenger RNA. It's a small piece of nucleic acid, similar but not exactly the same to DNA. And our bodies take that RNA and convert it into the protein subunits directly. So we don't have to worry about adding all of those same preservatives. It's a much more stable process, and we still have the benefit of creating that immune response. So why do we have the issue here in the storage of the vaccines, right? Now we know, the Pfizer vaccines have to be ultra low storage at minus 95. And the Mrna vaccine is at minus 25. The reason why those vaccines have to be stored at much lower temperatures than typical, say, influenza virus subunit vaccines is that RNA is just inherently more unstable than proteins are. And so from that process, we have to maintain the stability of the RNA so that it's viable whenever we try to insert it into the body for that process of translation to occur. So the advantages of using an mRNA vaccine as opposed to using a subunit vaccine, even though it has the same level of protection and prevention of infection, is that we're creating the proteins on our own. So that is going to hopefully provide us with some long-term support. And we're taking out a step in terms of the need for the preservation of those protein subunits. The other advantage is that it's very easy to modify these messenger RNAs. So if we start to see there being some changes, some mutations in the coronavirus and the development of, God forbid, a COVID-21 that was to develop, then we would potentially be able to very readily change that messenger RNA sequence for incorporation. And that's much faster and easier to do than to change the protein subunits in a traditional subunit vaccine like influenza virus. So that was sort of a long description there, and I see some of my former students on there. Shout out to Haley and Anthony Pham, talking about missing my lectures there.
I know, when you came on, the viewer count spiked. I was sitting there counting. I'm like, I need to have her on more often.
What, Jimmy? I see you out there. And Kelly Sampson out there too.
So, well, that's good. Who was it? I can't remember who it was. A while back, not last year, maybe last year, a year before, I don't remember. I did a quick run on our social media during March. They were doing the March Madness stuff, and I wanted to do a spin-off of that, so I did March Madness, mad scientist, like IRL mad scientist. And there was one, I can't remember his name, but he wanted to prove that, or he wanted to try to contract a virus to show something. I can't remember what it was. And so he would cut himself and push in human vomit and feces. He would eat it. Do you know who I'm talking about?
I don't.
The problem was whichever virus or bacteria it was, in those particular states was deactivated. And so he could never catch it, no matter how many times he did that.
Yeah.
He never caught it because it was deactivated in those particular environments.
Yeah, I mean, that's, one of the things that's important to note, very often we get questions like, well, why can't they just create this vaccine? Why is it taking so long? Why can't they do this? The development of these vaccines have to be very specific and unique to each individual virus, and in some cases, each strain of the virus. Doesn't appear to be the case for coronavirus, but for many viruses it is. And it's not something that is easy to do. One, it's somewhat of a guessing game to figure out which one of those proteins on the surface of the virus is going to be the one that is the most, what we call antigenic, the one most likely to cause an immune response to occur. So we know that there are going to be some differences there, but there are so many different viruses and variations of viruses. I mean, it's no different than plants and animals in the universe. There are just so many various forms and alterations that it's really hard to understand the ins and outs of each one of these. Because viruses are what we call intracellular parasites. That means they actually have to enter not just into our bodies but into our cells to replicate. That process and understanding how they get in and then how they replicate is critical for our understanding of how to stop it. So it requires a lot of effort for scientists to understand that process of what we call attachment and then entry, to understand how best to create a system that blocks that from occurring. The best way to do that is to have an immune response that prevents the initial attachment, if that's at all possible. But because of the diversity of the field of virology, it's really difficult to to find all of these differences. It's as now being the dean of the College of Arts and Sciences, I often talk about how art and science are so interlinked together, right? I mean, scientists have to be incredibly creative and artistic in the way that they approach the development of some of these very ingenious solutions, like creating a messenger RNA vaccine when a protein vaccine isn't functioning the way that we want it to. So each small piece that we uncover, each small piece that we place on this big puzzle is what helps us come up with that ultimate final result. So there's often times when we think about a mad scientist, and many times those tactics can be quite unconventional. Sometimes those are the ones that are ultimately going to rise up to the top and be something quite unique. But I don't know if rubbing fecal matter into an open wound is going to rise to the top of that heap. I hope not.
Yeah, I hope not too. Thank you so much. That was incredibly informative, and you doubled our viewers.
Yeah, well, I see Roderick, Matthew Jester. I think I saw Zach Banderas pop in earlier, so that's great.
Yeah. You want to stick around, or you got to head out?
Yeah, no, I can stick around for a little bit.
Okay.
I'll let Danny pop in, and I'll be here if anybody has any questions.
Awesome. Sweet. Thank you.
Happy New Year.
So, Dr. Rivera coming back in. Since... Keep coming. I'm not getting paid for this. I got to deal with your nonsense.
You aren't?
No.
Sally bought me ice cream, so I'm good. She said, you do this, I'm going to get you ice cream.
Nobody bought me ice cream.
Okay, so...
What was your next thing? I'm sorry.
I'll have you here. I don't know if they're going to be as informative as Fran's thing.
I know, right?
Like
That's not hard to do.
Okay, so I'm going to go with the other side. Instead of biology, we're going physics. So, this year we actually achieved one of the big challenges in applied physics, which is room temperature superconductivity. That's one of the big things that we need if we are to move to the next stage in material science and just in society in general, basically. So what is superconductivity? When you have a material, you have electrons moving from point A to point B, which is basically how you move electricity around, how we get our light bulbs to turn on and all this other stuff. There's always some loss of energy in the form of heat, in the form of friction.
You can't do that, man. We're live.
Okay, in the form of heat. When you have a material that is a superconductor, then your energy loss tends to go to zero. There's no collisions of atoms or electrons or anything of that sort, which makes energy transfer incredibly efficient. Like it tends to go almost to 100%. That'll make for better, much cheaper electricity. It allows for better transportation and just communications, antennas, all these other things. So it is one of the big things that we want to develop. So this year they actually had this material made up of hydrogen, oxygen, and sulfur. So very basic elements, nothing too fancy. They made up this three-dimensional structure that actually does superconduct at room temperature. There is a limitation though, and that is the pressure limitation. It has to achieve almost the same pressure as the center of the Earth. That is a huge number. I think it's like in the gigapascal.
It was in the
area.
tens of gigapascals.
So that makes it incredibly impractical. I know. I was selling this whole thing and it's not really gonna work. But we had two limitations, temperature and pressure. We removed one of them, temperature. So now we're halfway there, more or less.
I mean, that's great if we want to journey to the center of the Earth, right?
Definitely, you're gonna have superconductor. You're probably gonna
Do
die
you want a
across
stool or
there.
a chair?
No.
Okay.
You probably die there due to the pressure, but you're gonna have some really cool superconducting material there.
So you see, I'm sorry, I didn't mean to interrupt.
No, it's good.
You'll see superconductors used in practical purposes, usually for their magnetic fields. A superconductor has zero, by definition, zero electrical resistance. In the old days when we first started doing superconductivity or doing superconduction and investigating it, I've been in what, like the 50s or 60s or so, if my memory serves ish. We had to use pretty pure elements like copper and stuff. The problem is copper superconducts at 4 Kelvin, which is really, really, really cold. And you had to use liquid helium and then boil the liquid helium to cool it. I mean, it was just a big process. Through material science, we get these, you have to use ytterbium. I don't know, you have to use a bunch of different elements almost in an alloy fashion and create these ceramics. And we were able to do superconductivity at, say, 170 Kelvin or so, which is great because liquid nitrogen's temperature is in the 70s of Kelvin-ish. Is that right? That sounds too low now that I'm saying it.
I think that's the number.
I think it's 67 is the actual.
Yeah. 4 was helium, and then you went from liquid helium to liquid nitrogen.
The liquid nitrogen is really easy to do, really easy to make, really cheap, and so it was good for us, but you still have to have these ridiculously low temperatures. And so what happens is, with this, now we don't even need that. The highest temperature they hit was 300 something Kelvin, which it worked out to be just under 60 degrees Fahrenheit, which, I mean, we could have with that superconductivity in this room. It's kind of chilly in here.
Pretty much, yeah.
And they were hoping to stabilize the crystal lattice structure because once the pressure was relieved, the lattice disintegrated. So, I mean, you didn't have to have these weird elements. They were pretty common things.
Yeah.
If you could we could figure out a way to maintain that structure, we could use that. And so where are you going to see that? In practical terms, right now we're using superconductors in our MRIs. It's a superconducting magnet. It's a very controllable, extremely powerful electromagnet that's pretty small. And we could talk about transportation, or you mentioned transportation. I mean, your maglev trains. If we could shift those to superconductivity, they'd be really fast and cheap.
Yeah.
Computing. I mean, everything is going to change once this flips to being room temperature, stable superconductivity. And honestly, I really didn't think I would see room temperature superconductivity in my lifetime. I really didn't.
No, me neither.
And we did it this year, 2020. So, another thing that I was really hopeful for and really excited about this year was something else I didn't think I would see. There's a running joke in physics that we're going to get nuclear fusion. We're close to it. We're going to get it in 10 years. Every year. Every year the joke is we're going to have nuclear fusion in 10 years. And it's been that joke for like 20 or 30 years. Well, this year, I mean, we've the way that I tend to describe it to my class is think of an engine that's kind of stuttering but doesn't fully run. Right? It doesn't actually turn over. We've done that before, where in our fusion reactors, it's stuttered. We're talking milliseconds at longest, and we were excited to get that. Right? But this year, we hit fusion temperature, fusion density, right? What was it, 20 seconds?
20 seconds.
For 20 seconds. We're talking from thousandths of a second to 20 seconds. And that's phenomenal. So what's the deal with nuclear fusion there? In terms of energy, right, what's one of the main sources of energy that we're using today?
Fossil fuels.
Fossil fuels. What's the problem with them? We're going to run out?
Eventually, yeah.
They're releasing
Greenhouse gases.
greenhouse gases, they're pollutants. I mean, we're stuck on these things, right? We have the technology. I'm going to sound like the $6 million man. We have the technology.
They smell weird.
And they smell weird. Yeah, they do.
If you get a little in your hand,
I don't think that's like one of the big cons against fossil fuels. I'm just putting that out there.
I don't know. It's a pretty big con to me.
So our fossil fuels, right, are restricting. And we need to get rid of them. We have the technology today to move away from that, and that's nuclear fusion. Fission. That is splitting large atoms. If you look at the periodic table at the bottom, you have uranium. Right? We can purify some uranium types and some uranium isotopes and actually split them and release energy. Per gram, if I get a gram of that nuclear fuel, that uranium, and a gram of gasoline or whatever other form of energy you want, that nuclear fuel will produce thousands of times more energy than a gram of any other type we have. We have the technology today, we're using it today, and we could expand on it to move away from fossil fuels permanently. Like, well, what about, nuclear waste? Nuclear waste is just uranium that we haven't finished using. After one cycle, and I don't know if you realize this, after one cycle in a reactor, where they take the fuel rods out and put fresh ones in, those fuel rods are only 4% used.
Wow.
There's 96% fissionable material. Other countries recycle, the U.S. stockpiles. So after a few cycles, other countries have put old rods in. Why? It's 96% pure fuel. And so we have this issue like we're stockpiling this stuff. So, I mean, we have some issues with fission, but at the end of the day, we could do it. Right? We could build more fission reactors and move away heavily from fossil fuels. Get the electric cars, have your electric grid system based on nuclear fuel, and we're there. I mean, there's a ship. I think you were going to mention it. That is going to be nuclear fueled, a spaceship. Didn't we see that at some point?
I think most of them do have some sort of reactor at some point. So, quick question. What's the difference between fission and fusion?
That was my next point. He reads my mind. We spend way too much time together. So, fusion is something we haven't been able to do. Fusion's kind of one of the holy grails in science. Stars fuse in their cores. That's what's producing energy in the sun. That's producing sunlight, the heat. Everything is from fusion in its core. That's actually what's supporting the weight of the star itself, is the fusion in its core, in which hydrogen atoms, ions, slam together through a few processes and release energy as they do so, and they fuse, and through a chain of events you wind up with a helium nucleus. Okay? That's our goal. Why? Fusion is a lot cleaner and a lot more efficient than fission, which is what we can do now. Now, what we have works, and we can continue to do it and expand on it drastically as a stopgap measure, okay, until we can get fusion kicked off all the way. So we could take hydrogen and fuse it fuse them together in a reactor. We just get them moving really fast and really close together, and they start slamming together, and you start forming helium. So the byproduct of fission, right, is energy and some radioactive waste, which we don't like. The steam you see coming out of the big reactors, that smoke, that's not pollution. That's actually literally just water steam because they're hot. They're not polluting anything. They're actually really clean. They don't leak or anything like that. But for fusion, the only byproduct is energy, or byproducts, is energy and helium. We're running out of helium anyway. Helium is not something that's going to be around for forever. And so that would be a great thing, you know. The balloon industry could really cash in on fusion.
Yeah, I think they're waiting on that.
They are. They're totally waiting on it.
Fusion reactors, come on.
And so where are we going to get the hydrogen? Water, right? You can split oxygen and hydrogen from one another in water through electrolysis. You can combust them back together to release energy. The problem is the energy you put into it to split them is the exact amount of energy you get out to put them back together. So hydrogen fuel cells, yeah, you got to collect the hydrogen and you combust it with oxygen. Byproduct is water and energy, but literally you just get as much energy out as you put in. There's zero efficiency. But with fusion, we could dissociate the two, or break the water molecule, collect the hydrogen, and get thousands of times more energy slamming these things together than we could combusting them with oxygen. We're on the cusp of that. It's not 10 years away anymore. Now, I mean, for 20 seconds, it might not seem like a long time, but in the world of fusion, that is incredible. And we did that. Humanity did that in 2020. What else you got?
Well, it's kind of like making a star.
Yeah, so, I mean, literally what we're doing is we're making the core, the heart of a star on Earth, in a lab. That's literally what it is.
Nice.
It is.
Definitely. That was 2020. Okay, so I have another one here.
I'll grab my next one.
So, we have, for the first time, actually it was Singapore that first approved for commercial use. They're going to be selling lab-grown meat. So what is lab-grown meat? Correct me if I'm wrong, please. I'm not a biologist here, so I might be a little bit off. So basically you take a few cells from an animal. In this case, they grabbed chicken and they did a small biopsy. They took a few cells from the chicken and they started growing it, replicating it in the lab until they have a mass big enough to eat, basically. They're doing chicken nuggets, actually. Chicken bites, they're called. It's just chicken bites.
Not a nugget.
It's a bite, yeah. I think there's a patent issue there. So it met, this is an American company actually that's growing this. It met all of the benchmarks that Singapore has to clear them for selling them as an actual product. You can buy synthetic chicken, I guess, or lab-grown chicken. I don't know how they're going to market that to make it sound appealing, but they are doing it.
Test tube chicken.
Test tube chicken, maybe. It does have like, hey, are you going to test tube chicken?
That would be a good restaurant idea.
I think so, yeah.
Nobody steal it. That's ours. Test tube chicken coming to a corner near you.
Probably Cajun test tube chicken.
Test tube chicken. Put some Tonys on it.
Yeah. So they've been playing with this for a while now, but it wasn't until this year that they managed to perfect that technique. They had a few. They did beef before, but they said, and I don't know. I just know what they said, that the taste was kind of off. Apparently, lab-grown burgers are not the same as normal burgers. There was a thing there. But now they are molecularly the same, and apparently, according to the experts, they taste the same. So I guess I'll have to try one to see. They're going to be selling it, I think, starting next year, but now in 2020, they actually cleared it. This is a big benchmark for us, I mean, all jokes aside, because now we're dealing with a sustainability issue. Our population is growing really, really fast, and our farmland is actually shrinking, so we may not have, in the near future, enough food for everyone. So being able to produce our own, not having to have like farms for meat or for other type of just food in general, is actually one of our biggest challenges. So the fact that we were able to clear this and actually declare that it is safe enough for human consumption in a big scale is actually a big deal, and it happened in 2020.
Climate crisis also is a big contributor to the shrinking of food crops, the destruction of food crops. I mean, we've had, you get more and more severe storms as a product of climate crisis. climate crisis traced back, of course, to our greenhouse gas emissions as part of it. And so we've got on two fronts attacking the same problem. We've got lab-grown meat that is literally the same meat, just in the lab, just like lab-grown diamonds are literally the same thing. It's just made somewhere else. And then we're moving towards cleaner and more efficient fuel types like wind energy, more efficient solar energy and stuff. So we're making huge strides as humanity as a whole, as a civilization, towards being able to sustain ourselves for future generations. And that's happening and happened in 2020 with everything else bad going on. Another thing that happened is, and you'll have to forgive me, I'm not a biologist and certainly not a biochemist, a team of researchers, I can't remember where it was, developed an enzyme, or tweaked an enzyme, I should say, to break down plastics that are not typically biodegradable. And they broke them down within a matter of days. We have a huge plastics problem. Right, it doesn't break down. I mean, you can watch the news, you can see the sad stories of the animals. I do not recommend it if you've got a soft heart. I don't recommend it if you have a hard heart. I mean, the things that plastic is doing to the environment as a whole is just, it's bad. And with this enzyme that specifically targets plastic and breaks it down to something biodegradable, that's incredible. I mean, we found microplastics. I was reading last week, there have been microplastics found in amniotic fluid, which is really scary because that's us. I mean, the stuff is everywhere. So if we can get rid of it in a better way, that's great. I mean, plastics make it possible, as they used to say in the 90s, and now we can help curb that pollution issue. I mean, you got the huge garbage patch in the Pacific. I mean, it's just incredible. I mean, it's gigantic. So we're making strides to making Earth better, while the virus tried to make the Earth worse. We're making strides to make it better. Science. It's for you. You have anything else?
I have a last one. So this one, last but not least, we found or they found, actually it was a while back, but they didn't reveal it until this year, for reasons that I'd rather not say. Okay, can I say them? So they found this huge cliff, 8 miles long, 8 miles in
Kilometers.
length. Kilometers?
Or was it miles?
I don't know.
I thought it was kilometers.
Okay, 8 kilometers.
It's really long, either way.
Yeah, a really long wall of really old paintings. So they have this, such as the cave paintings they found in France. They found something very similar in Colombia. They date back from 12,500 years ago, so they're really, really old. They're believed to be painted by the first people that actually got to South America, that actually arrived there. They settled in around that area. It's close to the Amazon forest, so the southeast of Colombia. And it was really interesting. They actually found it a while back, let's say about a year ago approximately, but they wanted to do like a whole documentary on it, so they were filming before they released the news. But they did release it this December, so a few weeks back, I think. So that's really interesting. It rewrites a little bit of our, let's say a lot actually, of our understanding of human migration in general and just world history. So 2020 actually is gonna make us print a whole bunch of new history books.
It literally rewrote history as far as North America.
Oh yeah, it did. Definitely a lot of really interesting things. It gives us a little bit more context where we're from, and just it's really interesting to know all of this.
Yeah, definitely. So 2020 really is going to rewrite history and the future, and not just because of the virus or the pandemic. Jimmy asked a question. He said, "What happens to the oxygen if water is used for fusion?" I don't know.
It goes into the atmosphere.
Pretty much. Well, I mean, you could collect it and use it for things.
Yeah.
I mean, if you're going to collect the hydrogen, I mean, if you think about it, when we first discovered oxygen, that was what's his face, Lavoisier.
That was you.
Wasn't he the one? It was the British guy, and then anyway, it doesn't matter. If you do electrolysis with water, Oxygen is going to collect at one terminal, hydrogen is going to collect at another terminal. All we need for fusion is the hydrogen, so what you do with the oxygen is pretty much up to you. Now, I'm pretty sure, the setup to separate the two is the same basic principle, but a lot more sophisticated. So I'm not sure how the collection chambers are going to go, but you wouldn't actually inject the water itself or both the water and the the hydrogen and the oxygen into the chamber. The oxygen would get very much in the way of everything, and you can fuse oxygen. I'll say it now. There's no way that we're ever gonna get to that point.
Will we need to?
No, we won't need to. Hydrogen's the most efficient when it comes to fusion, anyway. And so yeah, we could just take the oxygen out, use it for something else, and put the hydrogen into our chambers, and then somehow collect the helium. I mean, we made a joke about balloons and stuff, but in science we use liquid helium, gaseous helium for a lot of applications, and it's getting kind of scarce. So that would be a boon for us.
Yeah, in industry, it's actually common practice to take all your side products, and if you can, you just resell them. Like CO2 is sold like it's a product combustion. You just grab it, trap it, do a CO2 trap, and then just sell it to soft drink companies. I'm guessing that something very similar is going to happen. You're going to have an oxygen trap somewhere, and then you're just going to sell it to pretty much anyone that wants oxygen tanks.
Mm-hmm. One last thing that I had, I'm reading off of my list because I couldn't get my iPad to cooperate with me. I have no idea what's going on with that.
Well, we have it in 2020. You can say that.
One of the things I want to talk about and kind of mention, we started this thing off talking about a few of the discoveries, just listing them. Something else that I had forgotten about was in the world of paleontology. Again, we're going to have to rewrite some books here. Paleontologists discovered the first soft-shelled eggs that have been fossilized. All the fossilized eggs to this point have all been hard-shelled. I have an egg, a fragment of a Saltosaurus egg at home. I gave it to my daughter. But they've all been a hard-shelled egg. A nest was found very recently that was fossilized soft-shell eggs. Think like sea turtles or snakes and things like that that have a very soft egg. So that was a first of its kind. Another first in another nest, or it might have been the same nest, but I don't think it was. I think it was another one. There were eggs that hadn't hatched, and in the eggs were perfectly preserved Tyrannosaur embryos. And so we have our first real good look at fossilized embryos from the Mesozoic era, from the time of the dinosaurs. So it's absolutely incredible. Do you have...
So we can do like a Jurassic Park thing here.
Funny you should mention that. Another thing that was done was, and this is something that I didn't have on my list because it's kind of one of those speculative areas. Scientists, paleontologists believe they have actually isolated dinosaur DNA from amber. So the whole Jurassic Park route. They're not entirely sure, and they can't be 100% that it's from an actual dinosaur itself, or from just, something other than a dinosaur. I mean, they had more than just dinosaurs. But there is a very good possibility that we now have dinosaur DNA in our possession, and I hope we don't do anything stupid with it. But
well, it is 2020, so
it is
for another day.
For another day or so, please don't let them do anything with that DNA for another day or so. So yeah, do you guys have anything else you'd like to add?
I think it's just too much to mention. I just grabbed a few that I thought were really interesting, but
absolutely,
so many things happened. Well, we were in lockdown basically. Science just kept moving forward.
Pretty much,
cool. Yeah.
Science always moving forward. One thing I liked about 2020, and the difficult part about the pandemic was, from a scientific standpoint, was watching how science played out in the news. Now, somebody mentioned here, one of our colleagues, something that hadn't dawned on me. We're all scientists. We're all used to seeing science done this way. You try something, it doesn't work, let's change it, right? I start off my low level, my 1,000 level courses with in science, a fact is something that we know right now, but we can change it in 5 minutes as we get new information. And so we saw a lot of scientists saying things, a lot of science facts coming out during the pandemic. And, excuse me, it changed, like, especially in the early pandemic, like every day, every other day. And that confused a lot of people. And I'm like, well, why? And then I realized we're used to seeing it like that because one thing the pandemic did was it allowed a glimpse from the general population, the general public, to see how we do science. It's literally a, let's try this. Okay, this worked. This is how it is. And then the next day we're like, oh, wait, no, that was wrong. And it's a process of going from thing to thing. Like Dr. Lemoyne said, over time, technique to technique, just trying different things out. So the pandemic gave a really good glimpse of how science is actually done, not televised or Hollywoodized or anything like that. I wish it was as simple as, hey, let me put this in the machine, push a button, come back 4 hours later, there's our killer. It doesn't work like that. What you saw during the pandemic was actually how it would work. And so that was incredible. Like the vaccine. I mean, we've never had a vaccine come out this fast, this effective, in less than a year.
And that this is the first widely used mRNA vaccine.
Wow.
Which does have some people concerned, but the potential is just amazing.
I'm telling you, 2020 was a rough year for a lot of reasons, but it showed that humanity can come together when, the going gets tough. We really pull together and push through, and I'm not so worried about our species anymore. I mean, we tend to really we're like cockroaches,
Some more than others.
Some more than others. Awesome. Aubrey asked, what would you like to see happen in science in 2021?
A few things, actually.
Go ahead.
So I actually saw a piece of news that's there's just a few observations that have happened now, but this is going to be a big thing in 2021. They discovered this fungus that grew in Chernobyl. I don't know if you guys are familiar with the area. It's in Ukraine, and it's the site of the most disasters, or the biggest disaster in nuclear energy. Reactor melted, or there was a meltdown in a reactor, and the whole area is just radioactive. This fungus, everything that is not radioactive resistant dies. This fungus not only grew, but it actually thrived in there. So they studied it, and it has some properties that we haven't seen before in fungus. It actually is resistant, or they believe is resistant to radioactivity. So it might have some really interesting applications in space exploration. So one of the big challenges when you're going to space is radioactivity. You don't have the same protections that you do on Earth because we don't have an ozone layer that travels with us. So this fungus might provide a key or an insight into how to protect ourselves when we're traveling beyond Earth. So that's one cool thing that I'd like to see in 2021. Something I look forward to.
Do you think Tenactin or other athletes' foot sprays would get rid of that? I mean, can you imagine a radioactive resistant fungus getting on you? How are you going to kill that?
You gotta go saw on it.
I don't want to see the toenails that come out of it.
What would you like to see in 2021, science-wise?
I think that there's been a lot of, renewed interest in studying, exploring areas that haven't been explored here on Earth. And I think that some of the really interesting things that are being done right now is the identification of new species in deep oceans.
I love that stuff.
And what that, just the potential for finding, geothermal microorganisms and what we can use that for. I mean, that's where the creativeness of science really comes into play, where somebody might just look at it and say, oh, that's neat, that's a bacteria that can grow in 120 degree water, and a scientist can say, well, I bet I can use it for this.
Exactly.
And so I'm excited to see what new species of microorganisms, plants, animals that we're going to be able to identify and figure out a way to just make humanity better, push our limits.
So I watch Octonauts. So I am up to par, up to snuff on my marine biology. That's how I knew about Siphonophores. When I read that article, I'm like, I know what that is. Because Captain Barnacle saw one. And I also learned about this lake in Antarctica that it leaks out, but the water is so iron rich it's actually blood red from the rust, and so as it leaks out and freezes, it looks like it's frozen blood waterfall. But in the lake itself, it's been frozen and untouched for millions of years, and these microorganisms, you think, okay, no oxygen because it's gone with the iron, it's bonded with the iron and everything. I mean, it's literally a rust water thing. There's nothing there, but it actually found microbes that thrive in that, and that they actually eat the rust. That's their energy source. And like you said, with the hydrothermal vents, you have non-photosynthetic life. I mean, you have chemosynthetic stuff. It's absolutely phenomenal. We've got these incredible regions that, like you said, we need to explore. I mean, we've not even explored 5% of our own oceans. That's insane. We know more about outer space than we do about our own oceans. It's easier to see space, but for me in 2021, I would like to see a raise. No.
I gotta go.
I don't know. I really don't have any expectations, any goals. Part of my background, I always tell my students, I joke, I was like, I used to be a good scientist, now I'm just a good teacher, and even then, depending on who you ask. But back in the day, when I was in my research prime, one of my big projects, in fact, the one that I wrote for my master's, was a Laser Interferometer Gravitational Wave Observatory, or LIGO, which discovered gravitational waves for the first time in 2015. They found a lot of black hole mergers that generated gravitational waves. To be honest, when I was on the project, we didn't think those were like strictly prime candidates. Really, Christopher?
Nope, it's chemistry.
Nope.
You're gonna say physics? Really?
I was gonna say physics.
With a straight face.
I can't. So anyway, we found that black hole mergers we thought weren't going to be that common. We actually thought neutron stars would merge more often, that there were more of them out there, so they would statistically merge more. And that wasn't the case. We found more black hole mergers. And then this year we find neutron star mergers. I'm like, hey, finally, after almost 11 years after I've done my research, we're finally finding these things. And then they find neutron stars that merge, and with the ability to this new astronomy, this new gravitational wave astronomy, this new way to see the universe, they were actually able to show that these neutron stars merged into a black hole that should not exist according to every theory. It exists in what we would call a forbidden zone in terms of its mass. It doesn't. A black hole of that mass shouldn't be physically possible, and yet there it is. And so I'd like to see more unique astronomy come out through our gravitational wave observatory. That's just kind of going back to one of my wheelhouses, one of my areas of expertise. But in general, I don't know. I kind of like y'all's answers. That sounded a lot better. Hey, it's going to benefit humanity. I'm like,
don't you look forward to the study of Brutinos? Maybe.
Can we leave the Brutinos alone? I'm really hoping for fusion to really. That's kind of my big hope for 2021 is to really see fusion take off. Okay. Thank you guys for watching. Thank y'all for taking time out of your lives. Well, your life.
I have ice cream. I'm good.
Stop rubbing it in. We will see you in another session. We plan to do these more often. We have a lot of fun with them, and people seem to enjoy them. We're getting good feedback from them. So with that, goodbye 2020. Happy New Year, everyone, and we'll see you later.